Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. So today I will be sharing my research findings entitled the Sombor Index and Sombor Polynomials of a power graph for some finite groups. My name is Nuaida binti Adimun from UiTM Pasir Gudang. So this is my joint work with Professor Dr. Nurhaliza Samin from UPN, Dr. Sanhat from Iraq, and also Dr. Nabila Najmuddin from USM. So basically, this research is under the pure mathematics research for the applications in graph theory and also group theory. This is my presentation outline. First, I will start with a brief introduction in topological index, group theory, and also graph. And then for literature review, I'll be explaining the definitions and also propositions that will be used to prove the main theorems. And then we also have results and discussion, conclusion and recommendations, list of references, and lastly, the enrichment. So let's move on to introduction. So what is actually topological index? So topological indices are numerical values that reveal the important details related to the connectivity or topological structure of a molecular network. So basically, topological index has been introduced first in chemistry, and then in chemistry, we have a molecule. So they want to know the properties of these molecules without involving any laboratory work. So in order to know the properties of the molecules, we need to convert the molecules into a number or a numerical value. So in order to get a number, we need to first link the molecules into the molecular graph in graph theory. So in graph theory, we have many types of graph. So based on the graph that we have obtained, so we will study the properties, which include the degree and also the distance of the graph, and then we substitute into the formula of topological index. So from the value that we will get from the topological index, they will predict the physical and chemical properties of the molecules. The topological indices also play a crucial role in various fields of chemistry and related disciplines, including drug design, chemical property prediction, quantitative structure activity relationship, QSAR, QSPR, and recently I also found a study that they analyzed the vaccine of COVID-19 by using topological index. So there are many types of topological index have been developed since 1947. So the first topological index that has been developed is Wiener index. So we have two types, distance-based topological index and also degree-based topological index. So under distance-based, we have so many types of topological index, but I only put three here, Wiener index, Zagreb index, and also Harawi index. And then for degree-based, we have Randall index, Zagreb index, and also Sombor index. So I will focus on Sombor index only in this study. So let's take a look on types of graphs associated to groups. We have many types of graphs that have been introduced. So these are some of them. Non-commuting graph, contiguous graph, power graph, and also cofront graph. So each types of graph has their own definition. So in this study, I will only focus on power graph. So these are the three groups that involved in this study, which are the Heidegger groups. We have also generalized quaternion groups. We have quasi-Heidegger group, but we focus on only non-abelian groups. So these are the group presentation. So each group has a group presentation. So let's say we look into the Heidegger group. So the Heidegger group is denoted as D2n. So 2n is the order of the Heidegger groups. So the Heidegger groups is generated by element A and B, where an is equals to b squared is equals to 1, bab is equals to A inverse. So same goes to generalized quaternion groups and also quasi the Heidegger groups. But the relations for different types of groups are different. So let's take a look for literature review. 1947, Harold Wiener introduced the Wiener index and computed for subgraphene. So actually, he introduced the Wiener index and then used the Wiener index to compute or to predict the boiling points of some paraffin. So in 2021, Gartner developed a new topological index called the Sombor index. So actually, within 1947 to 2021, there are so many topological indices have been introduced. But recently, in 2021, Gartner developed the new topological index called Sombor index. Cross et al. Characterized the graph's extremum with respect to Sombor index. In 2022, Muhammadi et al. Found there is good correlation between the Sombor index and molecular mass of alkene, and aniline series. 2023, Kasher et al. Introduced the Sombor polynomials. The Sombor polynomials is the extension from Sombor index. So I include also the definition, important definitions that we need to know before we go to the main result. First, we need to know what is Sombor index, what is Sombor polynomials, and then what is graph, what is the definitions of power graph, and some propositions that have been found from previous studies. So definition 1, Sombor index. The Sombor index of a graph is equals to the summation of UV in the H of gamma square root degree squared U plus degree squared V. So U and V must be adjacent to each other. So adjacent means the vertex is connected to each other. Okay, same goes to the Sombor polynomial, but the difference is we have x to the power of degree squared U plus degree squared V here. So x to the power of integer, because degree squared U is integer plus degree squared V is also integer. So we need to know what is complete graph because the generalized power graph for 3 types of groups include the complete graph. So a complete graph is an undirected graph in which every pair of distinct vertices are connected by a unique edge. So in a simpler way, we can say that each vertices in a graph is connected to each other. So what is power graph? A power graph is an undirected graph with 2 distinct vertices x and y are adjacent if and only if they are the power of one another. Okay, these are the examples of power graphs of the Heidegger groups for certain orders. So this one is the Heidegger groups of order 6, the Heidegger groups of order 8, the Heidegger groups of order 10. So you can see here that the number of vertices and also the number of edges are increased when the order of the Heidegger groups are also increased. So from the construction of these power graphs, so they come up with generalizations of the power graph of the Heidegger groups of order 2n. So we don't need to consider the group presentation of the Heidegger groups and then the definitions of the power graph to construct the graph. We just use this generalization. So this one is the complete graph. It's the complete graph where the vertices is a subgroup holistically of order A. So we have E. Let's say we have the Heidegger groups of order 6. So n is equals to 3. So we have E, the element E, A, and also A squared here. So they are connected to each other, and the rest of the elements will be here. So from the graph, we can determine the degree of each vertices, E, AI, and also AIB, and then they also generalize the power graph of generalized quaternion groups of order 4n. So this one is the complete graph, and the rest of the vertices will be here. So let's go to results and discussion. So from the graph, from the power graph of generalized quaternion groups of order 4n, we can determine the degree of each vertex, EAI is to AN, and also AIB. So we actually use the properties in the graph and also the generators in the Heidegger groups presentation so that we can come up with this degree E, degree AI, S to AN, degree AIB. So we generalize it so that we no need to construct the graph to compute the Sombor index or Sombor polynomial. So from the degree itself, we can straightforward get the degree of E, degree of each element. Okay, for proposition 5, we determine the number of edges is equals to n times 2n minus 1 plus 5n. So we just substitute the n value here. So let's say we have Q4 times 2, Q8. So n is equals to 2. So just substitute 2 here. Just straightforward, we'll get the number of edges. So no need to construct the graph. And then we come up with this power graph of generalized quaternion with this quasi-Heidegger groups QD to the power of n. So this is the complete graph, and then the rest of the elements will be here. So from the graph, we determine the degree of each vertex. So we come up with this. Degree E is equal to 2 to the power of n minus 1, and then degree AI is equal to A to n minus 2. degree AIB is equals to 1, degree AGB is equals to 3. So this is the condition. So next, this is the main result, Sombor index, and also next we will go to Sombor polynomial. The Sombor index of the power graph of the dihedral groups is equals to this formula. So this looks very easy, but actually it requires a lot of understanding in graph theory and also group theory. First, you need to understand the dihedral groups, the relation in dihedral groups, and then construct the graph. And then some propositions and also properties of the graph we need to know. And then from the pattern of the graph and also the edges, we can determine these theoretical results. And then based on the same technique or the same method of proving, so we come up with this theorem 2 and also theorem 3, the Sombor index of the power graph of generalized quaternion groups, and also Sombor index of the power graph of the quasi-dihedral groups of order 2 to the power of n. So theorem 4 is Sombor polynomial, so it's quite longer than Sombor index because we cannot simplify it further since we have x to the power of something. Because when x to the power of something is not the same here, so we cannot simplify it. And then theorem 5 we have the Sombor polynomial for power graph of generalized quaternion groups Q for n, and then this is for quasi-dihedral groups. It's a little bit longer, but I believe that when we know what is the value of n, we just substitute it into the formula. So no need to take your time to construct the graph of the group from scratch. So you just need to use this formula. And then conclusion and recommendation. So in this study, the generalizations of the power graph for the quasi-dihedral groups are found, and then the general formula for the Sombor index and Sombor polynomial of the power graph associated to some finite non-abelian groups are determined, and the results are very useful to analyze and predict the chemical and biological properties of the molecules. Some recommendations are other types of topological indices for various types of graphs can be investigated. And then another new type of topological index is also possible to be developed. So these are the list of references, the acknowledgement. So thank you. That's all from me.